Alright class, let's go ahead and solve this problem 835. Basically it's telling us that insulated piston cylinder device contains of 0.3 meter cube saturated refrigerant, right? So the volume of the refrigerant is equals to 0.3 meter cube, and then the state 1, the pressure was 0.6 megapascal, 0.6 megapascal, so we recorded this one. And then the refrigerant now allowed to expand, right? Expand in a reversible manner. This is very important. So it's a reversible process until the pressure drops to 0.6 megapascal, and determine the exergy change of this refrigerant. Now um, so we know that the pressure at state 1 0.6 megapascal, and pressure at state 2 0.16 megapascal, and also a surrounding temperature 25 degrees C and 100 kilopascal, right? So it is asking us that what is the exergy change between state 1 and state 2. So some of the assumptions for this problem: it's an isolated system, first of all, right? Insulated system. That means that for insulated system, it's actually, let me write it, it will be insulated, insulated system, right? For insulated system, it there is no heat transfer from that system, right? So that means it's adiabatic, and also reversible manner. That means that it's also isentropic. If a system is reversible as well as adiabatic, then the system becomes isentropic. And then negligible stored energy, and we can see that it's a closed system. There is no kinetic energy and no potential energy as well. So at state 1, which is equals to P1 equals to 0.6 megapascal, with respect to that, I went through the table A11 to A13, and then got all those values, right? So for example, for 600 kilopascal and saturated vapor, refrigerant vapor, I got the specific volume, this one, right? I got the internal energy, and I also got the entropy. So now we don't know about the how much refrigerant is. We just know the volume, right? So let's determine the mass. So mass of the refrigerant M equals to volume of this refrigerant divided by specific volume, right, which is V1. So 0.03 meter cube, and we got this one 0.0 we got this one 0.34335. So this is meter cube, and this is meter cube per kg, right? So it will become kg. So M equals to basically 4335 0.8737 kg, right? So this is the mass of the refrigerant. Now let's go ahead and determine the thermodynamic properties at state 2, right? At state 2. So at state 2, we have the pressure, which is equals to 16 megapascal, 0.16 megapascal, right? So with respect to that pressure, and entropy is also remain constant, right? It's an isentropic process. We can get the all those excuse me, we can get all those thermodynamic properties, right? For example, entropy of the refrigerant SF equals to 0.12686 kilojoule per kg, and entropy of that liquid vapor SFG equals to 0.81517 kilojoule per kg Kelvin, right? And then we know that specific volume, we have 0.007435 meter cube per kg, and specific volume Fg equals to, this is Vg equals to 0.12355 meter cube per kg, and the internal energy UF equals to 31.06 kilojoule per kg, right? And UFG equals to 190.31 kilojoule per kg, right? And let's write the UG as well, which is 2 to 1.37 kilojoule per kilojoule. Okay, so we have all this information. Let's determine the entropy at state 2 first. Or we know that entropy at state 1 and state 2 is the same, but we don't know the quality of the refrigerant, right? So S2 equals to SF plus X2 times SFG, right? So X will become S2 minus SF divided by SFG. So if I plug in all those value and determine, which is 0.9754, right? This is 97% the quality. So V2 equals to VF plus X. So this specific volume V2, this one equals to X2 times VFZ, which is equals to 0.12 053 meter cube per kg, and U2 equals to UF plus X2 UFZ. Plug in all those values and we get 216.69 kilojoule per kg, right? Now for reversible work output, right? If a system has reversible work output, the Exergy change for that system we just derived in the previous class, that the Exergy input minus Exergy output, and definitely it's for excuse me, it's for closed system, right? Exergy destroyed equals to Exergy of that system. So this is the Exergy balance, right? So here the Exergy is Exergy destruction for reversible process, it's 0. So meaning that Exergy in minus Exergy out equals to Exergy in was x1 and Exergy out is x2, right? So that means Exergy change of that system, basically the useful work, right? Or the reversible work, or reversible work, right? So I can write it W reversible, which is equals to x2 minus x1, right? So W reversible equals to x1 minus x2, and we know that this relationship equals to phi 1 minus phi 2 for W reversible, right? W reversible, so phi 1 minus phi 2 is nothing but the mass times U1 minus U2 minus T naught of S1 minus S2, right, plus P naught of V1 minus V2, right? So since it's an isentropic process, S1 and S2 is the same, right? So W reversible will become, we got the mass times u1 minus u2 plus mass times, or let me write it this way, it will become p naught of p1 minus p2, right? So let's just plug in all those values. W reversible, which is mass equals to, we got 0.8737 times the internal energy we got at state 1 241.86 and 216.69, right? Plus, and the pressure of that system was like P naught, which is the surrounding pressure, right? Or the dead state pressure, which is 100 kilopascal, times P1 we got 0.034335 minus 0.12053, right? So if I solve this one, W reversible, which is 0.8737 times 241.86 minus 216.69 500 times 0.03335 equals to 14 kilojoule, right? So this is the answer for this problem. So the Exergy change, or the reversible work output of that system, which is equals to 14 kilojoule. So that's the answer for this problem. So that's all about the Exergy change for a closed system. I mean, we can similarly solve the problem for Exergy for the flow stream or open system. Basically the difference will be right here, this formula, right? So this formula, other than that, I think everything is the same. All right, thanks for watching this video. We'll come back with another lecture.